So hi, I'm Matteo. The plan for today, as she mentioned, is to introduce you to the fundamental ideas behind TensorFlow, as well as give you some examples and some tips that will help you while you're doing your assignments, and also give you a demo of Colab, which is the environment you will be coding your assignments in. And finally, we'll have some time at the end so that you can try out Colab and come to us and ask us questions if you have some issues with it and you have problems, for instance, connecting to the backend that actually runs the computation. So what is the fundamental idea in TensorFlow? So TensorFlow is a framework that is composed of two main parts. So the first part is a library. It's a library that is used to define computational graphs. And the second part is a runtime that allows you to execute these graphs across a variety of different hardware. Computational graphs, if you're not familiar with the concepts, are an abstract way of describing computation as directed graphs. And in these graphs, the edges correspond to data, to multidimensional arrays that flow through the different operations. And the nodes represent these operations, which either create these data, these arrays, and these tensors, or they manipulate them according to specific rules. And so what's the advantage of computational graphs, and how do they compare to a standard program? So a standard program is mainly constituted by two things. It's a collection of primitive operations together with an order in which we want these operations to be executed. And of course, there are many other things you might think. There are functions, there are classes. But all these things are basically abstractions. At the most fundamental levels, this is really what a program is about. Instead, computational graphs are, again, a collection of primitive operations, but instead of specifying the order of execution, they specify exclusively the dependencies across these operations. So how the outputs of these operations flow from one operation to another. And this is quite an advantageous representation for a reason I will be explaining shortly. So on the left, for instance, you can see a very simple program where we instantiate a variable, we assign it a value of 10, then we create another variable, we multiply them, we take their sum, we take the result of these two operations, we divide one by the other, and we print the result. It's a very, very simple program. And the same set of operations can also be encoded in a more abstract form on the right, where we see that we have these ops, these operations, which in this case create two numbers, and the other combine them in different ways, and finally there is an operation that actually takes care of printing. And what's the advantage of the second representation, the one on the right? The main advantage is that we can do dependency-driven scheduling. So this means that operations that do not depend on each other in any way can happen in parallel, can be scheduled in parallel. And this means that by using the topology of the graph to drive the scheduling of operations, we can get much better performance by exploiting, at best, the capability of our hardware. So for instance, nowadays, each of you on your laptop probably has 8 to 16 cores. And by representing your program and the operations that you want to be executed in this form, you can easily assign, the backend of TensorFlow can easily assign the different operations which do not depend on each other on different cores and just execute them in parallel. So you get really high performance with very minimal input from the person who actually writes the program. So let's see how you can define such a computational graph. Saying again in this extremely simple example, on the left you can now see the TensorFlow equivalent of the same program. So in this case we are defining a tensor that is a constant of 10 and another tensor which is a constant of 20. These are two operations that generate these pieces of data. And then we define an operation for each of the ones that we had previously. So the addition of these two numbers, their multiplication, and the division of the results. And the key issue here is that when you execute the program on the left, this TensorFlow program, no computation is actually happening. When you get to the end of this sequence of programs, you don't have actually computed the result of these operations. You have only defined and declared which operations you would like to have executed. And then it's a separate step, the one of actually executing your computational graph, performing all these sequence of operations and getting out results. And this is the same difference between declarative programming and imperative programming. And it's a difference that can take a little bit of time at the beginning to get used to, but that is very powerful because it enables to do very interesting things. So in the TensorFlow terminology, the operations, these nodes in this graph, are called ops. And the data that flows between these ops are referred to as tensors. And in general, these tensors will be basically multidimensional arrays or tuples and nested tuples of multidimensional arrays. So the one important thing is that TensorFlow doesn't just allow you to implement simple computational graphs like the one I showed you. It actually supports very general forms of computation. So it includes stateful, conditional, iterative, and asynchronous computation from first principles. And all these forms of computations are directly enabled by specific inbuilt ops, which you can use and you can to define this type of computation in your graph. So we'll have variable ops. These are ops that allocate some space in memory and then allow you to read and write values to this space in memory. And these values will persist across different executions of this graph. Then we have conditional ops, which allow you to make some part of the computation conditional on the result of some other part of the computation. So you could, depending on the result of a certain part of the graph, either execute some portion of the graph or a different portion of the graph. You have loop ops. These allow you to efficiently specify computational graphs which have cycles. So you can, for instance, have loops and iterate the same iteration until some condition is satisfied, all without leaving the computational graph. Control ops allow you to enforce or some additional handcrafted order in the execution of pairs of ops. So in some specific cases, the data-driven dependencies are not enough. You might want to explicitly say that before some op executed, some other op must have completed its execution. And there are specific ops that allow you to specify these additional constraints. And finally, there are queue ops, which allow you to describe asynchronous computations in a very clean and effective way. So until now, all the simple examples I showed you only focused on declaring and describing this computational graph. But every single TensorFlow program actually is constituted of two parts. So there is the declaration of the graph, and then there is the execution of the computational graph or of some subset of the computational graph. And both these parts happen within Python. So you have a Python interface to TensorFlow that you can use to define computational graphs as a TF graph object. And then you have other Python utilities that you can use in order to trigger and schedule execution of these portions of the graph through what we call a TF session. So let's start with the TF graph. So the TF graph combines and describes all the computations that you have defined through these abstractions of ops and tensors, where tensors are just a description of these multidimensional arrays that flow between operations. And they may have shape and a data type, but they don't have actual values. This is really the most important thing that you need to remember when you're writing TensorFlow. When you define a tensor, that doesn't allocate anything in memory. There is no actual computation going on. And this is very intuitive if you think of this simple example. So let's define it in a matrix of a trillion by a trillion in TensorFlow and in NumPy. So if you do it in TensorFlow, that is a perfectly defined thing to do. You can define a matrix of zeros of a trillion by a trillion. But until you try to execute this op, and therefore the backend actually tries to instantiate to this trillion by a trillion zeros, everything is perfectly fine. Well, when you, in a standard scientific computing library when you define a matrix of a trillion by a trillion, that means that you're actually instantiating that amount of memory, and it's just an out-of-memory error. So this core distinction between declaring and executing is really what you need to keep in mind, because these two parts live within the same program, because you're using the same language both to define and then later to actually execute. One interesting feature of TF graph is that beside accumulating all these TensorFlow ops and tensors, it also does what we call shape inference. So if you define some tensors and then you define some operations on them, the TensorFlow graph will try as much as possible to propagate shape information across different ops. So if I take, for instance, a matrix of a 10 by 10 matrix of zeros, and I concatenate it with himself or along the first axis, I get another tensor back. And this tensor, even without executing, I can already ask what shape it has, because TensorFlow will just infer the shape from the input tensor and the specific op. So this is on the other part of TensorFlow. So the sessions is our interface to the TensorFlow runtime. So the part of TensorFlow, of the TensorFlow library, that takes care of scheduling and executing ops across your different hardware. And a session is what carries out the actual computation. And on the left, you can see a simple example of using a session to perform some operations. So we define a simple graph again. This is just defining 3 tensors, which are just constants, and then another couple of ops which add the first 2 and then divide the first 2 by the third. At that point, when you arrive to the 4th line, no computation has actually yet happened. And then is after the comment, there is where we actually perform some computation. This is where we define a TF session object, and then we can ask this object to execute specific portions of the graph. In this case, we are saying session run D, the tensor D. And the tensor D is the division between the first 2 and the third. And there is where the computation actually happens. And you can both request execution of a single op, so as in this case, or as you can see on the right, you can also request execution of multiple ops at once. I request the evaluation of multiple tensors at once, and then it will just trigger all the execution in a single pass. When you speak about sessions, the most important thing you need to remember is that TensorFlow identifies and executes the smallest set of nodes which need to be evaluated in order to compute the tensors you're requesting. So in this case, everything needs to be executed, because in order to know what D is, you need to divide the addition of A, B plus C. In order to have a C, you need to execute that constant. In order to get the addition of A and B, you need to execute both A and B. So just by the natural dependencies in the computational graph, by requesting an evaluation for the tensor D, TensorFlow knows that needs to execute the entire graph. But in other situations where you have much more complicated graphs, this might not be the case. So when you request the execution of a specific portion of the graph, not everything will necessarily be executed. So you will have maybe just a portion of the graph that gets executed, which is the minimal portion needed to evaluate the tensor. TensorFlow comes with binding for multiple programming language. So Python is the main supported language and the one we will use in this course. But it's good to know for future reference that you can actually interface TensorFlow across a variety of different languages. So there is C++ interface, and C++ is actually what implements most of the backend of TensorFlow. And then there are Go and Java support, although in experimental state, from the TensorFlow team, as well as support for other languages such as Haskell and Rust, which are supported exclusively by the open source community. And the choice of the language in which you interface TensorFlow is not as crucial, because Python is convenient, and we chose it for this course because it has a lot of open source support. There are a lot of other libraries for data science and machine learning which are implemented in Python. But the language you choose to interface with TensorFlow is actually just what you use to declare the graph and to request executions from the graph. But most of the computation and all the heavy lifting actually happens in the highly optimized C++ backend. So the choice of the language you use to interface TensorFlow is not as crucial for performance in many situations. So until this point, we have seen different constants, and we have defined different operations in different ways. But each execution of the graph would always give you the same result, because if you take two constant tensors A and B and you sum them, every time you execute that operation, you'll get the same result back. Variables are instead what enables learning by preserving state across different executions of the graph. So all the trainable parameters of machine learning models, for instance, will typically be TF variables. And a variable is defined by a name, type, shape, and initialization procedure. So, for instance, you can declare a variable, as in the example, which shows how to declare a variable which is a matrix of floats, with 2 by 2, and which is initialized using just a random normal distribution with a specific standard deviation and a mean of 0. And once you have defined these variables, then you can use them within your computational graph, and you can define ops which update and modify these variables within the computational graph. So for reading the variables and using them within the computational graph, that is very easy because you can just use them as you would use any other tensors. So the variable v, which we defined in the previous slide, we can just, for instance, take the matrix multiplication of that variable with another constant matrix, as in the first example here on the slide. So you can basically reuse them interchangeably with tensors. However, you can also assign values to these variables, and then this value will be maintained until another update happens. And assignments are also ops, which are also exposed by the object itself. So you basically have 2 different syntaxes for doing assignment. In the first case, you call assign on the object, on the reference to the variable itself, and then you assign another tensor to it. Or in the second case, you can actually call the library assign op and just pass both the variable you want to assign and the tensor you want to place inside it. So, defining a variable adds that op to the computational graph. But again, just like with tensors, a variable instance actually exists and allocates memory and holds values only in the context of a specific session. So if you have, for instance, multiple sessions that use the same computational graph, the same variable might have different values in the different sessions, because the variable definition in the computational graph is just a declaration that you have a variable of a specific shape, type, and initialization. But it doesn't actually hold values until you try to execute it in a session. One thing you need to remember is that before using a variable in a session, you need to explicitly initialize it. So you need, and you can do it manually, but there are also shortcuts to just initialize all the variables in your computational graph, and this is an example. Suppose you have some function, create graph, that defines your big computational graph, and this includes the creation of some variables. Then you can create an op with the TF global variable initializers that, when executed, initializes all the variables inside your graph at once. And then once you have done that, there is where you can actually go on and use these variables in order to perform your computation. There is also an alternative. So instead of initializing the variables manually at the beginning of the session, you can also rely on a monitored session to do this for you. So the monitored session is basically a wrapper around the standard TensorFlow session that takes care of a bit of the boilerplate code that otherwise you would need to use in your graph. One of the things it does, but it's not the only one, is initializing the variables. So because when you have declared all the variables, you have to have specified a way of initializing, then the monitored session can just go through all the variables in their graph, call the appropriate initializer, and do this without you having to do the operation manually. One thing you need to remember, though, is that the monitor session doesn't only do the initialization of the variables. It has other side effects that you can see in the documentation, but the one of which you must be definitely aware of is that it finalizes the graph. Finalizing the graph means that any attempt to create additional ops and add additional ops to a TF graph after you have called the monitor session will actually raise an error. So if you need to first create all the computational graph and then instantiate your monitor session and use it to carry out the computation. Any questions up to here? Anything unclear? Cool. So variables are nice because now we have enabled our graph to express much more general forms of computation in which the result of an execution of the graph has an effect that persists in future execution of the graph, which is important if you want to do machine learning because you need to for instance, update the variables of your model in order to improve the performance of whatever task you're trying to address. But there is another important thing in order to be more general. The second important thing is that we need a way to feed the data into the graph. So if the data set is very, very small, in principle, we can just embed it in the graph definition itself. So we could load the entire data set inside the NumPy array. It's just a big matrix. And then we could define a TF constant, which is an op that every time it's executed, will load the entire array into and provide it to you as a result. However, this is really not a recommended way of doing this. And this is because, for multiple reasons, but the most trivial is that if the data set is of even moderate size, you'll probably run out of memory. And also, the whole data set will be serialized every time the graph is serialized. So if you store your graph somewhere, then also all the entire data set will also be saved within the graph definition, which is a very inefficient way of going forward. So there is a different and better approach to this. So if you need to feed input and data into your graph, and you need this data to change across different execution of the graphs, as it's very standard in machine learning where you want to feed different inputs at every update, then you need to use placeholders and the feed dictionary. These are two TensorFlow components that allow you to inject data inside the graph and do this at execution time. So you define a placeholder at graph declaration time, and you can use them within the graph declaration just as if they were other standard tensors. But at each execution of the graph, they will take a different value. They will take the value that you specify in the feed dictionary that you pass to the session.run. So this is a very simple example again. I define a placeholder, which is just a scalar. It's a float and it's a scalar, and that's all you need to know for the graph definition. Then I define another constant b, which is just a 0. And I define an op which takes these new numbers, sums it, and gives me back another tensor. And if now I instantiate a session and I run C, if I just run C without providing any value for A, this will give an error. It will give you a runtime error because it will tell you that it needs a value for the placeholder in order to know what A plus B is. But if instead you provide a feed dictionary, which is a dictionary that maps placeholders to numbers or NumPy arrays, then it will actually perform the computation and give you back the result you wanted. So for instance, if you feed a value of 3 for A, you will get back 4, and if you feed a value of 4, you'll get back 5, as it seems most reasonable. So what are the pros of placeholders? So using placeholders puts the onus of managing the data fully on you. So TensorFlow really doesn't care. So it just expects the dictionary of placeholders to NumPy arrays for each calls of session.run, and all the rest is up to you. If you want to load the data somewhere from file, you want to pre-process it, you want to batch it in specific ways, you want to queue it, all of this, if you use placeholder, you'll need to do yourself, which is not a big issue because typically this reduces to some matrix gymnastics, but it is an additional onus, an additional boilerplate code that you need to take care of. The advantage is that despite being a bit labor intensive, it is very flexible. You can literally pre-process your data in any way you want in NumPy, in Python land, and then just feed the data to TensorFlow to perform the computation of, for instance, the update of your model. However, you don't always need all this flexibility. Very often, the type of pre-processing and data managing that you have to do is fairly standard. In that case, TensorFlow offers additional built-in functionalities for working with data. So you have, if you look up TF data, this gives you all sorts of utilities for loading data from different types of sources, files, CSV files. All of this comes for free in TensorFlow. And if your use case is not too unusual, then typically the loading of the data will be taken care of appropriately by some of the built-in utilities of TensorFlow. Okay. So let's now, all we've seen up to now was very, very trivial examples. So let's try to make it slightly more interesting and consider a simple linear regression problem. And keep things easy, we'll consider a univariate regression, which is the problem of learning some function f from real numbers to other real numbers. And yeah, please.
Sorry to interrupt your flow.
No worry.
The feed dictionary, do you copy it across the boundary? Does it still get serialized, the data inside it?
So that's a good question, but the answer is no, because when you serialize the graph, you serialize just the definition of the graph. So you serialize that there is a placeholder, which is a float, and it's a scalar. But the value that the feed dictionary assumes, that's not part of the graph definition. That's something you provide at runtime and might be different at each execution, as in this case. So when you serialize the graph, the placeholders are extremely lightweight because they don't actually contain any data.
So you don't copy it into an area managed by TensorFlow at all?
No.
You refer to it by pointer?
So at graph definition, yes, you only refer to it as a reference to some specific, a reference to some tensor which is generated by this placeholder. And at execution time, that's where actually this placeholder needs to have some memory allocation because it actually is fed in some data from the feed dictionary. But there is no additional, like, at graph definition time, there is no allocation of memory in terms of for the values of this placeholder. So when you need to just serialize it, you really don't need that. Yeah.
Does your value of C persist between the two session.runs? So in the second one, you were to feed A as C from the last one, would it?
No. So the answer is no. And the reason is that the only things that persist across execution of the graph are variables, and although it's a bit less common, queues. So everything else, like tensors, do not have a value outside of an execution of a session.run. So when you request execution of some tensor, then all variables are evaluated, all feed dictionary and placeholders are evaluated, and then the TensorFlow sweeps through the graph, computing all the tensor it needs to give you back that number, and then it returns you that number, which you now have as a NumPy array in Python land. And then and nothing is persisted across the stateful components of the graph. Yeah.
Although if I'm looping and I assign the result of session.run to another variable and then use that variable in the feed dictionary,
then that will be fine. So you could, instead of printing it, you could say D equals the result of session.run, and then you could say session.run C feed dictionary A D, and that would actually reuse the variable as he suggested. Any other questions? Please.
Why else would you use tf.variable over placeholder in that case?
So the reason to use variables, we'll see it very shortly, but just to give you a brief introduction, these variables maintain values within the computational graph itself. So, and they are available for, in instance, if you want to compute gradients and derivatives of some tensors with respect to some variables within the computational graph, then you cannot do it if you define it as placeholder, because the placeholders, you cannot define gradients with respect to placeholders. So you really, if you want to use all the power of TensorFlow to compute gradients, perform optimization, and all of that, you really want to store the stateful components of your model within the graph rather than in Python outside of it. Yeah.
So if you feed a NumPy array into a variable, then you very quickly run out.
Sorry, could you repeat?
You said if you feed a NumPy array as a variable, you very quickly run out of memory. But then you said that if you were to use a placeholder, you could do a pre-processing in Python. So do you not have the same?
So the advantage is that, so what I was speaking of was something like, something like this, where you define the entire data set as a huge matrix. So this would give you probably run out of memory as you try to evaluate this up. The advantage of doing it in Python is that typically you won't just define a huge NumPy array in Python, but you'll probably have some way of reading through the data, and you would probably read a portion of the data set, put it into a matrix, feed it into TensorFlow, then read another batch of data from the data set, put it into a matrix, and feed it into TensorFlow, possibly using utility code that you can find open source for doing this in a synchronous manner, and this allows you to prevent the problem of running out of memory. Anything else up to now? Okay. So let's consider this simple problem. As I was saying, univariate regression aims at learning a function from real numbers to other real numbers, and to learn this from data. The key aspect of univariate linear regression is that we assume that that function is linear. So in univariate case, we assume that both the input and the output are just a single scalar. What does it mean that it's linear? It means that there is this that the data satisfies this relationship where the output can be computed just by multiplying the input by some scalar value and then summing some offset. Typically, in the data itself, this relation will actually not hold. So it's rare that the data itself is exactly linearly, but for any data set of pairs of inputs and outputs where both are scalars, you can find values for W and B in the linear equation that minimize the error, the mean squared error on your data set. So you can find a specific pair of coefficients such that if you use those coefficients to predict the output from the input, the average squared error on the data set is minimized. And and this is often many circumstances is enough, because maybe the discrepancies and the error that you see come just from random noise in the data set, and you don't really want to fit all of that necessarily. So the linear function finds the best possible trend, the best possible linear trend that explains the data. So in the univariate linear case, then you can actually find these coefficients in just closed form. So there is an equation that gives you the best values for both W and B for a given data set. The two values that minimizes the prediction error on the data set. And these are the equation you can see on the second line. If you consider that x bar and y bar are just the mean of the input and the outputs respectively, this amounts to just summing over the data set the product of the difference between inputs and the mean input and the output and the mean output, and dividing it by the variance of the input. And there is this even simpler equation for finding the coefficient b. This is very convenient because it means that you can, in one shot, just get out the best linear fit to your data. Just by applying that equation. However, it is also not a particularly general approach. So it works for linear functions and linear models, but it doesn't generalize to big complicated models. So a more general way of solving the linear regression problem, which we will generalize to the kind of models we'll see and we will use in this course, is to use gradient descent to iteratively improve our estimates of W and B. So many of you, I assume, will be familiar with gradient descent, but just to recap, what you do with gradient descent is you update each parameter by subtracting some fraction of the derivative of the loss function, in this case the mean squared error, with respect to that parameter itself. And this leads you to a simple update rule for both W and B that you can apply iteratively until convergence, until you converge on some values which are an optimal fit for the data. And this kind of solution, this gradient descent solutions and its variance, generalizes to problems where the closed form solution doesn't exist, or it's too computationally expensive to solve, which is also a quite common use case. So in order to address this problem with TensorFlow, first of all, we need a data set. So let's consider a simple data set where we generate data according to the following rule here. We basically take a few inputs, just equally spaced, and then we basically multiply them by a coefficient, add some offset, so this would give us a perfect linear relation between input and outputs, but then we add some random noise, just some Gaussian noise with zero mean and unit variance, just to introduce a bit of discrepancies in the data. And then the problem we will try to solve in the next couple of examples is how to find the best linear model to fit this data. So in order to do so, first of all, we need to create a simple linear regression model. So just to separate the definition of the model from the training of the model, I've here defined a class. It's a linear object, a linear class that when you instantiate it defines two variables, a variable for the coefficient and a variable for the offset. And these variables can be updated within the TensorFlow graph and will persist values across the executions. At the beginning, they will be initialized at 0. And until we update those values, those variables will maintain a value of 0. If we, during a session.run, we update these values to some other variable, to some other value, then we'll get some different linear model. And the linear model itself, it's defined in the call. So once we instantiate this object, we will call the object in order to actually build the linear model. And this will be just multiplying that variable by the input tensor and adding up the offset variable. It's a very simple model. What we will do first is now trying to solve this model in closed form, which will be a bit clunky, and then we'll see how we can also solve it with gradient descent in a much more neat and efficient way, which generalizes to much more complicated models. So let's define the solver as part of the graph itself, just to make it a bit more interesting. What we need first is two placeholders. We need a placeholders for the inputs and a placeholders for the outputs. Then we instantiate our model, and we connect our model to the input tensor, to the input placeholder. When we call the model on the input placeholder XDF, this call function that executed. So we create a tensor which is equal to the product of the placeholder times W plus B. We then get back from the model a model output tensor, which will give us predictions for each of the inputs in the placeholder. We can then define what the optimal values for W and B transposing the equation that we had here just in TensorFlow language. So what we need is just to sum and compute sums and compute means. And this is what we do with this simple code here. So this is the numerator to estimate W, and this is the denominator. In the first case, we take reduce mean in order to compute the mean of the outputs, reduce mean of XDF in order to compute the mean of the inputs, and then we multiply them and reduce sum to actually get the sum. We can do the same with the denominator and get out the tensors for W hat and B hat, which will be our estimates of W and B respectively. These will be the W and B which minimize the error in our input data, which is not yet defined in the TensorFlow graph. So this is a function of what we feed in as the placeholders. We can feed any data, and TensorFlow will give us back the best W and best B. And then what you can do is, always remaining in a TensorFlow graph, also define ops that update our model itself. So we can define an op that takes the variable W and assigns our best estimate for it. And or we can define an assign op that takes the variable B and assigns the best estimate for it. And this will give us, and if we execute in a session.run solve W and solve B, we will get the solution to our linear regression problem for every given set of inputs and outputs pairs. And this is what we do in this example. So right here, we are defining MonitorSession. So this is initializing all the variables for free without us having to take care of it. It's finalizing the graph, so we cannot anymore modify the ops itself. We can still modify the values of the variables during the execution of the session that runs, but we cannot add the new components to the graph. And then we call session.run on solve W and solve B, feeding in the input and outputs that we have created in NumPy using this simple code here. When we do this, what we get is that the TensorFlow backend executes the entire graph we saw here, because in order to execute solve B, in order to assign, it needs to know the value of W hat and goes all the way backwards, computes all the graph, computes the optimal W and B, and assigns it to the variable. From then on, in all future execution of the graph, until we actually call again solve W and solve B, until we actually change in some way the variables of that model will persist, will keep those as values for W and B. So we have a trained linear model that we can use to make predictions. And this is what we do in the second session.run, where we compute the model outputs for those inputs to get a visualization of what our model is actually representing, and this is the line you can see on the right. And as you can see, it's a sensible fit for the data we have. Of course, it cannot fit all of the inputs-outputs pairs because the data itself has this Gaussian noise and it's not perfectly linear, but it does get very closely what the underlying trend is. Any question up to here on this example? Please.
So in the second one where you put preds, the reason it doesn't sort of recalculate W and B is because it knows it doesn't have to in order to calculate the model. It's clever enough to.
Yes, exactly. So basically what TensorFlow does is goes to model output, which is here, and executes everything that is required to compute model output. And solve W and solve B, so the reassigning of the variables, is not required in order to compute model output, because model output is just this call here. Is W, which is a variable which persists its values across execution, B, which is also a variable, and X, which is just the current placeholder. So all the rest of the graph, because it's not required, required by any dependency to be executed, will not be executed, saving computation and giving you the results you would expect.
In the second case, when you're calling the model output, you don't actually have to feed in the YTF.
Yeah, that's a very good point. The YTF actually is not needed. So because you don't need YTF in order to compute the model output, it's not used. If you don't feed a value to the feed dictionary, the TensorFlow will perfectly will not request you to do so. So the only values that you will need to provide in the feed dictionary is the values for all placeholders, which are used in order to compute the tensor you're requesting in that specific session.run.
Is there a reason why, for your linear model, you don't, your variables are defined in its init method,
Right.
but you assign those variables values outside the class?
You could define a linear model which has an update method, which basically includes all of that code. That's perfectly fine. Okay, so this is the example of how you would solve linear regression with closed form. But really, this is not how you will ever train models within this course. So, but it is a good example in order to start getting to understand how you can code and describe computation in TensorFlow. So now let's focus on gradient descent, since this is what we will be using mostly. Before going into there, I want to point out another huge advantage of using computational graphs, this abstract representation, and this is that it allows you to very easily compute gradients. So if we know the gradient of the output of an op with respect to the input of that op, for every primitive op, which comes for free in TensorFlow, then the chain rule provides us a way to compute gradients for any tensor with respect to any variable in the graph, as long as there is a dependency between those. And the reason is that computing some tensor from some variable eventually amounts to some form of compositions of functions. So by just using the chain rule, you can, and knowing the gradients of the individual ops, you can compute the full gradient with respect to a tensor to some other variables, which possibly is used very, very far away inside the graph. And you can do this fully automatically, so you don't need to write your gradients. While in this example, we didn't have gradients, but we wrote the solution to the problem manually within the graph. This is really not necessary in most cases when you do gradient descent-based algorithms, because TensorFlow can infer and compute the gradients directly from the structure of the graph itself. And this process is known as reverse mode auto-differentiation. And it not only allows you to compute the gradient with respect to a tensor and any variable in the graph, but it does so in a very efficient way, because you can do this basically in a single sweep with a backward and forward for the graph. And despite being automatic and not requiring you to actually write down the gradient manually, it is not like numerical methods. Because numerical methods are a way of computing gradients in an approximate way, without writing down the equation, just by computing the finite differences between valuations of some function. While autodiff is actually giving you the exact gradients, the real true gradients, just for free in an automatic fashion. So how does automatic differentiation work? as I said, is just an implementation of the chain rule, but it also has a very neat graphical representation. You can map the chain rule to basically very simple and clean operation onto the graph. So basically, if you want to compute the gradient of some tensor with respect to some variable in the output, let's say a and b are the two variables. If you want to compute the gradient of this with respect to a, you only need to compute to multiply gradients along the path from the output until the variable you want to compute the gradients for. If, however, in your graph there is a cycle, there are multiple paths that lead to the output tensor you want to compute a gradient for, then you need to multiply along the paths and sum where paths join. And this is basically just the chain rule, but it's graphical representation. And you can do so, then you can immediately see that computing the gradients for this tensor with respect to any of the variables just one forward and backward pass for the graph. Any questions on this, please?
Is the differentiation done symbolically at graph definition, or is it depending on the values that get fed into it?
It depends on the values you feed into it. So it will multiply the gradient with respect of this with respect to this for this input times the gradient of this with respect to its input for that specific value.
Sorry.
Yeah.
What's the advantage of this reverse mode autodiff versus, I guess, the forward mode autodiff?
That it gives you all gradients in a single pass through the data. You just do a forward, and then you do a backward, and you have all gradients, and you reuse all the computation. Like, the evaluation of this node is needed both if you want to compute the gradients with respect to this and the gradient with respect to this. And if you go backwards, you can just reuse all the derivatives you're computing and do it in a single nice sweep. While the forward mode is a bit more convoluted. So this is a typical form that people use. It's basically also what backpropagation is all about. Of course, it's perfectly valid to also just write down manually the derivatives and just compute all the equation and write down that as part of the graph itself and then apply the gradients. That's not wrong in any way. They give you the exact same results. The advantage of this is that if your model is huge and very complicated, doing all that manually might not be particularly complicated, but it's a lot of computation, very boring, and you probably might get it wrong at some point, and then all your results will be off. Well, if you do this, you can rely on the well-tested arithmetic differentiation tool to just infer from the structure of the graph itself what the right gradient is, which is convenient for big, complicated models. So how does this actually happen in TensorFlow? So what happens is that TensorFlow TF gradient function constructs that subgraph that implements in a specific way the auto-differentiation. And the nice thing is it does it in a fully transparent way. So the only thing you need to do is call TF gradients and specify the tensor and the variables you want to compute the gradients with respect to. So this could be the list of all the variables of your model. This could be the loss function. And then TF gradients would give you back the derivative of the loss function with respect to each of the variables. And so grads will be a list of tensor which has the same length of variable lists, because you'll have a gradient for each of those variables. And one thing you need, if the tensor does not depend on one of those variables, then that entry will still be present in grads, but will be none. So it will just figure out that there is no dependency between the two, so there is no gradient defined for that tensor with respect to that variable, and just return you a none for that specific entry. And finally, if my tensor is a multidimensional tensor, what happens is that the gradient is summed along those dimensions. So you don't get the Jacobian, you get the summed version of it. So we can also define the gradient descent solver as part of the graph. And in this case, what we need to do is to execute an update op repeatedly until convergence. And the graph we saw before was much more complicated, while here, because we are really exploiting the core functionalities of TensorFlow, we can get this very clean and very simple update rule. We define loss function as the difference between the model output and the outputs in the placeholder. Then we define the gradient of the loss with respect to the variables. And then we can just assign the hard-coded expression of the gradient descent. So the current value of the variable minus some fraction of the gradient, where that number 0.001 is what we typically call learning rate. We can also group these, so we can create an op that when executed executes both parts. And then calling this and actually training your model is just repeatedly calling that update op. So every time you need to feed the placeholders and call update. And you can do this, I don't know, 500 times. And if you log and if you print the various predictions along the way for a few different steps, you can see that the predictions start just with a random slope and random offset, and then slowly start to move up and align correctly with the underlying trend in the data. So there is also an alternative. So this is already pretty clean. I think you will agree that it's definitely much cleaner than it was defining closed form solution. But you're still doing quite a bit of boilerplate code, which is fairly standard, like just taking that gradient and assigning it to the variable one by one. So what you can do, and you should do, is use TensorFlow optimizers. So instead of manually computing the gradients and applying the updates, you use these high-level components, which inherit all are subclasses of this TF train optimizer, which implement all sorts of different optimization processes. So you have TF train gradient descent optimizer, where you just specify the learning rate, and or you can define other gradient descent optimizers that are much more effective in practice, such as RMS prop or Adam optimizer. These different optimizers do things like momentum or some forms of a slightly second order optimization, and the TensorFlow really gives you a lot of different built-in optimizers to play with, and that makes a massive difference when you have to actually train in practice big neural network models. So before I go to the next topic, any questions up to here? Sounds good. So, oh yeah, please.
What's the TF group?
TF group is just an op that when executed, like if you request the evaluation of update in a session.run, then TensorFlow will actually, is like requesting the execution of those. So it's just a way of, instead of doing session.run update W, update B, you can just say session.run update. Okay. So control logic. So up to now, we have seen stateful computation. We have seen how we can define these computational graphs and have them persist values across different executions. But there is more to TensorFlow computational graphs. So what we can do is also support conditional and iterative computation, as well as specifying additional control dependencies. So up to now, all the dependencies were purely the ones that were driven by the data itself. Like one op was using a specific tensor in order to compute its output, and therefore had to wait for that tensor to be available in order to be executed. And everything that didn't depend on each other would execute in parallel potentially, and would be scheduled by the TensorFlow backend in order to maximize performance, but without any specific prescribed order. With control dependencies, what we can do is add additional dependencies. So we can say, first do this, and then do this other thing. You don't need to specify a full ordering of all the ops, but you can add the specific synchronization points by using these control dependencies. TF-cons and TF-ks allow to specify conditional execution. So if the computation of this part of the graph gives you some specific value, then execute this, otherwise execute something else. And while loop allows you to write cycles within the TensorFlow graph itself. So let's take a simple example. We define a variable with a 0 initialization. We define an assign op, which assigns 10 to that variable. We define a tensor that sums 1 to the variable x. And then we execute z within a monitored session. What do you think will be the output? Any idea? Any brave person? there is an obvious answer. The obvious answers would be 11. And the actual answer is 1. So the reason is that you need to think about dependencies. We have asked to execute z. Z is equal to x plus 1. X is a variable which is initialized to 0. 0 plus 1 is 1. There is no reason by which assign x should be executed in this computational graph. We have not requested it. His output is not used anywhere. So TensorFlow will find the minimal subset of nodes it needs in order to compute z and just return you that. What you can do maybe is do this. What if I do assign x and z? What will be the output of this code? 10 and 11. The answer will be either 10 and 1 or 10 and 11. Why is that? The reason is that when you call a session that runs with a list of tensors, the order in which you pass these tensors doesn't matter. TensorFlow is not first calling assign x and then assigning z. It's taking all tensors that you pass to session that run and is doing one pass through the graph and trying to and scheduling everything as fast as it can. So depending on just a race condition, it might first execute assign x and then some 1, or first execute some 1 and then assign, first do 0 plus 1 and then assign 10. Because there is no dependency. These two things, now we are asking for both, but there's still nothing that prescribes in which order they should happen, so they might happen in any possible order. What you can do, if you want to specify an order, is do this. You can say, with control dependency of an assign x, do x plus 1. This means that if you ask even only for z, TensorFlow will know when it tries to compute z that before doing whatever is in this block, it must evaluate assign x. It will execute assign x, assign a value of 10 to the variable, and then some 1. And now you actually get a deterministic output of 11. So, any questions? I guess there will be.
Sorry, can we rename assign x to x so that we don't have to do that?
Sorry?
Could we rename assign x to just x and then...
Yes, that would be a valid way of doing it. So if the assign variables actually perform an assigning of the variable and also return you the new value. So instead of saying z equal x plus 1, you would say z equal assign x plus 1, then it would first compute assign x, return you a value of 10, and then some 1. It will also give you a deterministic output. Conditional evaluation. So this is what you need in order to make your computational graph conditional on other parts of the computational graph. So you have the tf_con_dop, and this makes the execution of whatever you define in these two functions conditional on the output of the switch in this case. So what does it mean? Basically, tf_con takes a Boolean tensor and two functions, where the two functions define the graph that you want to execute if the Boolean tensor is true, and the graph you want to execute if the Boolean tensor is false. So if you do this, you define two variables. You define a placeholder for a switch, so we can feed the true or false when we call session.run at leisure. Then we define a tf_con, which returns you the output of assigning v1 1 to v1, or the output of assigning 2 to v2, depending on the value of the switch. If then we call session.run on cond, and then we print the resulting values for v1 and v2, what we will get is, as you would expect this time, that v2 has a value of 2. Because we have said that switch is false, it didn't execute this part of the graph. It only executed the second part of the graph defined by that lambda. And so you get the value you would most likely expect. However, there is more fun to this. Because you might think, okay, I'll do an innocent refactoring, and I'll just create these assign functions here, and then I have a lambda just returns that assign up. If you do this, what do you think will be the output?
The output of the assignment.
Sorry?
The output of the assignment.
So the output will be that they both are the execution of both is triggered. So what happens is that all the code that you want to be executed conditionally should be created by the function you pass to the tf_con. In this case, the function we pass to the tf_con is not creating anything. The op has already been created outside. And this means that these two ops are a dependency of TFCon. And this means that if they are a dependency of TFCon, before even checking that condition, TensorFlow will execute both of them because they are both dependencies and must be executed. So both v1 and v2 will be assigned a value. And then it will check the switch and will return you v2 in this case because the switch is false. So it will return you only the second, but will also execute the first. And in this case, because the graph we're creating is actually an assign op, this will have a side effect that will persist. In other cases, if you don't have variable assignment within the TFCond, having dependencies that are not created within the function but outside will only be a waste of computation. But if you have assign ops, it will actually change the result of future executions. Please.
So TensorFlow, if you put ops in kind of any TensorFlow function, we should just assume it's not lazy, those are run.
No, they are run if they are dependency of something else. So they are run if they are used within something else. So typically, in most ops, it means that they're used, their value is directly used. But in the case of TFCond, this means that their value is potentially used. And that's enough to trigger execution unless you create it within that function and then it knows that it actually has to execute it only in one or specific case. You can also have cycles in the graph, so have iterative computation within your computational graph. And so let's see how this works. So this can also be a bit tricky, but it's very useful in a variety of situations. So let's go through this code in a bit more detail. So we define a constant of 2, and we define a matrix. This is just a matrix of ones. And we define a condition. So this condition is the graph that will be executed to evaluate if you need to do another iteration. While the body will be the graph that is executed at each iteration. And both the condition and the body will be passed to the same tensors. It just happens that the condition only looks at one of them, so I put an underscore there. And then you define a while loop by specifying, by passing condition, body, and initial values for the loop vars. The loop vars are the variables that will be passed both to body and the condition at each cycle. And at the beginning, they will have a value of 0 and just a diagonal of 1s. So what happens if you execute this code? What you get is that for k times, because at each iteration, this while loop will multiply that diagonal by the matrix M. So we'll be basically raising to a power by multiplying multiple times with itself. And then finally, when the loop var I gets to about at least k, then it exits. So the while loop will return you the final value for I, and the final and the multiplication of that matrix by itself for k times. This might seem a bit a contrived example. Why on earth would you do that? So the reason is that this is a very common and useful thing to do in a variety of situations where you have sequential data. You want to not process a single sample like in standard supervised learning, where you have IID samples and you just go through them once, and each update, each evaluation of a sample is independent by each other. You have situations where you have time series, or you have language. You have the way you don't want to process one input depends on how you process the previous input. And in this case, you want maybe to keep around the output of the previous computation, and you want to reuse it, and you want to iterate maybe for a variable length. So maybe you want to process one word at a time until the end of the sentence. And you don't know in advance how long the sentence will be. In this case, you need a way to just perform this computation for multiple times until some condition is satisfied. And this is where things like a while loop come handy. However, the while loop is fairly low level, so you don't always need to go all the way down to that. TensorFlow typically exposes both very low level APIs, very low levels utilities that are extremely flexible and allow you to do basically anything you want. as well as providing a lot of built-in function and built-in code that takes care of all the most common use case and the most standard situations. And this is also the case for here for these cyclic and iterative computations. So what is the standard setup when you do this kind of iterative computation in deep learning and in machine learning? The standard situation is that you have some transformation, which we typically speak about as a core, and which you apply recursively to some state, which is what persists and is accumulated along the way. So the core is a transformation. It's a piece of graph that applies some transformation. In this case, it's multiplying the input by some matrix. The state is what is accumulated along the way. So in the previous example is the kth power of that matrix. And the third thing that we typically have in deep learning and reinforcement learning is we also output things along the way. So after each time we take the previous state, we apply the transformation, we get a new state, and we get some output. Maybe the best guess at that step of the processing. And this is a situation, the same pattern applies across deep learning, when you do time series prediction, sequence-to-sequence models, but it applies to reinforcement learning, where you have to take decisions in partially observable domains. So if you have in reinforcement learning, you have these agents which must learn to perform some task and act in some environment. And in some cases, the environment is fully known to the agent. The agent just sees everything there is to know and to see at each step. In this case, it doesn't really need to memorize anything. It doesn't need to, at each step, can decide based only on his current information. But in most interesting domains, this is not the case. Maybe you have a first-person view. So when you look in some direction, you don't see what is happening in the other direction. And then you need, in order to know what to do while you're looking in this direction, you need to remember what the world looks like when you were looking in the other direction. So you need to have this persistent state which you accumulate along the way in order to take decisions in a partially observable domain. However, also in the reinforcement learning case, the same pattern works perfectly fine. You define a transformation which takes a previous state and outputs a new output and a new state. And this is why TensorFlow gives us specific utility for this use case, because it's really the most common that you will encounter. So in order to give you an example of this, let's take something that most of you will know pretty well, which is the Fibonacci sequence. So the Fibonacci sequence is a very simple sequence of integers where each element is the sum of the previous two. So the first two elements are 0 and 1. So the third element so the first element, each element is sum of the previous two. So 3 is the sum of 2 plus 1. 5 is the sum of 3 plus 2. 8 is the sum of 5 plus 3. And so on and so forth. And you can just generate all these sequences by just applying the same rule to this persistent state that you're moving forward. Because if you keep a memory of what are the last two, you can just go on and on and on. Yeah?
Are you missing a 1?
Yeah, there is a 1. Instead of the 0. And so what does the transformation you're applying look like? This is, as we said, is defined typically in TensorFlow terms by a core. So a core is something that takes an old state and gives you an output and a new state. So, and what does this transformation actually do? So you define the old state has the previous two elements. The output is just the sum of those two elements. And the next state is the new output and the second element from the previous state. This is a very simple transformation. You take the last two, you drop one, you sum them, and you accumulate in front. And how would you implement this in TensorFlow? It's actually fairly easy. What you need to do is define a Fibonacci core. A Fibonacci core is something that has an output size of 1. At each step, it always gives you the next number in the sequence, and has a state size which is actually has 2 dimensions, because you need to remember the previous 2 elements in order to continue. And what we do is then we can define the core, the same equation we had defined in pseudo code before, just like this. So we return the sum of the 2 elements of the state. This is the output at each state. And the new state, which is just the second element of the state and the new one. Then we can define the zero state and the initial state. This is what we need in order to for the TensorFlow utilities to work appropriately. And then what you can do is just this. You use the dynamic RNN, you specify a Fibonacci core, you specify some inputs, which we don't really care about, and a type, floats, time major. This just specifies whether you want the batch dimension or the time dimension. This is some technicalities, which you can look into more details later. But the core thing I want to show you is that just by defining the core, then you can get the unrolling for free. And this happens dynamically and in a very efficient way, just out of the box. And if you just run the TF dynamic RNN with a specific core, then you get the sequence you would expect.
Those are dummy inputs.
Yeah. And yeah, as you see here, the input is not actually used. But the dynamic RNN expects you that you take input, because in all practical situations, you won't just be updating the state without looking at the world. You'll typically be feeding as input, I don't know, the last observation in reinforcement learning, the last word that you read in natural language processing, or the last time step in some time series prediction.
So would it be, if you were unrolling an RNN in prediction and you want to use your prior predictions instead of some inputs, like in a sequence-to-sequence model,
right?
Is that where you're sort of using a conditional to?
That would be one. Yeah, that would be one way of doing it, for instance. Yeah. Okay, so these are really the core functionalities of TensorFlow, the ones we went up to now. However, TensorFlow is really a really powerful and huge library. So that supports a lot of things, because once you embrace this paradigm of declaring and then executing through a runtime, you actually can do much more things that just for free. So what happens is, for instance, that multi-threaded execution, this we partially already discussed, happens for free. Everything that is not has not a dependency on each other, TensorFlow will just try to execute it as fast as possible. If your computer has 8 cores, and there are 2 things that can happen at the same time, it will just schedule it on 2 different cores and get, therefore, a good multi-threading in a totally transparent way. You don't need to say, okay, create this thread, manage this thread. TensorFlow gives you multi-threading out of the box just by the fact that it's using this computational graph abstraction. But a bit less obvious, because we didn't mention it yet, is that TensorFlow actually enables you also transparent execution across different types of hardware. So it doesn't only support multi-threading, it also supports heterogeneous computing. So you might execute some part on a CPU, some part on a GPU, some part on an FPGA, some part on some other crazy device, because the abstraction itself is agnostic to this. Like, you define a computational graph. It's a very, very abstract view of the computation you need to do. And then TensorFlow, what it does give you, it gives you simple ways of annotating this graph and just saying, this op should be on this device, this op should be on this other device. And then the TensorFlow backend takes care of actually doing all the scheduling across the different devices. Another final really interesting advantage of TensorFlow is transparent distributed execution. So the same computational graph, just by annotating it differently, you can execute across multiple machines, and then the TensorFlow backend will also take care, again fully transparently, of communication across the machines. You don't have to do RPC calls yourselves. You'll just specify on what machines the different ops live, and then TensorFlow will send the data back and forth and just take care of that computation. And this is extremely powerful if you want to deploy some huge model, maybe in production, and you want to cross multiple machines. And this is especially powerful because one of the things that you can do, for instance, in a distributed way, is training of the model. So you could have multiple machines, each of which is sampling a batch, computing gradients, and then these gradients can be applied in a distributed way to a shared set of variables, either in a synchronous or in asynchronous way. TensorFlow supports both basically out of the box. So just to give you an idea of what I mean by annotating your graph. Annotating your graph means basically just putting these blocks where you say with TF device, create these ops. All ops created within a TF device block will be placed on that specific device. In this example, I'm just telling that I want those constants to live on the CPU, like the creation of those constants to happen on the CPU, and the matrix multiplication I want it to happen on GPU. And that's all you need. If your computer, if your TensorFlow is built with GPU support and you have a GPU in your machine, that's all you need. You will execute this code and you will pick the appropriate device based on the annotation you made. This config pass to the TF session. This is just what you need to do if you want to log what you are actually, where the different ops are actually being executed.
When you run C,
yeah.
Is it reading the memory from the CPU, from the constants A and B?
TensorFlow will send the data from the CPU to the GPU and then perform the operation.
Okay.
I'm not claiming that this is, a good split of the two things. It's just to give you an example of how you can separate out things.
Okay, but in the case the GPU doesn't have enough memory and you want to use the CPU for that, can you do that? Like if you're trying to, if you have something like really, really large, like 16 gig, for example.
Yeah, in that case, the GPU will you will probably not be able to execute that operation on the GPU. There are, however, ways in which you could do it. For instance, you could have that your data is so big because it's a big batch of data. In that case, you might execute half of the batch on one GPU and half of the batch on another GPU, and then just join the outputs of the two things. So there are ways you can then split the computation between. But if it's a single, monolithic matrix multiplication, then and that multiplication is so big that it cannot fit on a GPU, you are a bit in trouble. That's kind of not really TensorFlow issue. It's more, although there are specific ways in which you can still do partitioning, but they are much more complicated than just splitting the batch. So what will happen if I just do this? So what happens is that you don't need to annotate your graph. So TensorFlow by default has an automatic placement procedure that will try to do his best according to some heuristic and what it can and cannot do to assign the different ops to different devices. So in this case, it will definitely put on the CPU those two. But then if your computer has a GPU and you have built TensorFlow with GPUs, then this operation will actually be scheduled by default on the GPU. Even if you don't annotate it, TensorFlow tries to schedule as much as possible on the GPUs. If instead you don't have a GPU, then we'll just schedule it on the CPU, and that's it. So there is also an automatic placement system, and that's where this configuration comes handy, because you can just inspect where TensorFlow has decided to put ops, because sometimes they might decide to put on the GPU some operation which are fairly small and don't scale well and are actually better executed on the CPU. So it's good to, if you don't specify everything yourself, it's good to keep an eye on where TensorFlow is actually placing the different operations. So already in core TensorFlow, there are two levels. So there are both low-level utility functions, and there are higher level functions like the dynamic RNN utilities to unroll cores. There is actually quite a few core tools and libraries built inside TensorFlow, but there are also a host of different neural network libraries, for instance, built on top of TensorFlow at a much higher level of abstraction, which you can use in order to exploit all the power of TensorFlow while maybe making it a bit less boilerplate code and much simpler to reason about. So just two examples for future reference. One is Sonnet and one is Keras. Sonnet is the neural network library we use in DeepMind, and it's now open source. Keras is a neural network library which supports multiple backends. You can use TensorFlow as backend, you can use Torch as backend, you can use Theano, I think, as backend. And however, in this course, we will ask you to actually build neural networks with the raw TensorFlow, not to use these higher level libraries, because even if you do eventually use these higher level libraries, and we do every day in DeepMind, understanding the core functionality of TensorFlow and the lower level is important in order to use them in the appropriate and correct way. So I'll just give you a couple of data points about Sonnet specifically. So Sonnet is a TensorFlow library with two main aims. The first is give you a reference implementation and well-tested implementations of a variety of deep learning modules and architectures. And the second is provide you out of the box easy sharing of weights across modules. So there are a lot of situations where you want to reuse the same weights in multiple places. And this can be a bit tricky if you don't have a library that does this for you, because you need to construct the same graph in two places but reusing the same variables, and it can be a bit boilerplatey. So Sonnet gives you this out of the box by embracing this configured and connect paradigm, which is also what I had used in this simple example. So in the linear module, I have this configure and connect example. First I created the variables, and then I called the object in order to actually create the graph that performs the computation. And Sonnet gives you this, follows this the exact pattern. And the only thing you would do in order to change that into a Sonnet module is inherit from abstract module. And then you can actually you don't really need to instantiate things separately in an init. You can just use this inside the definition of the graph itself. And then Sonnet, because you are inheriting from abstract model, would take care behind the scenes of actually making sure that it doesn't create different variables every time. But every time you call this object, it creates a new graph, but that shares variables with all the previous ones. So it's convenient when you need to share variables effectively. And finally, before switching to Colab, I just wanted to point out that nowadays there are many deep learning frameworks available. There is Torch and PyTorch. So these are two different interfaces to a common backend in Lua and Python respectively. There is Chainer, which is also in Python, Caffe, which is C++ and Python interface, and Theano, which is similar in some ways to TensorFlow. But the latter is not supported anymore, but it was maybe in some way a precursor of Tensor, because it follows a similar declarative approach in which you define the graph, and then this graph gets compiled into execution. And all of these have pros and cons, and share quite a lot of features and have some differences. And in terms of raw performance, it depends a lot on the model. So some models will run faster on some specific backend, some will run faster with others. But if you're speaking about single machine, it's probably comparable, many of these. What TensorFlow gives really an edge on is if you want to really not just play with the model and prototype it, but once you have a model, just scale it up. You want to put it in production, you want to scale it up across thousands of machines. Like, it basically gives you all that for free. So all the distributed and the multi-threading, the parallelism, the different devices, all that is extremely transparent to the users. So it really enables you to go from just simple prototyping to actual production code really easily. So now that's it for the first part. And now Alex will be talking about Colab and how you can use it in order to do the assignments of this course. Is there any final question you'd like to ask on this part?
So the next 20 minutes are going to run you through Colab, which is what we're going to be doing all the assignments in for this course and what you're going to be using largely to develop when you're running TensorFlow. So can I get a quick show of hands? Has anyone used IPython Notebook before, or Jupyter Notebook? Okay, great. Well, we're coming from a pretty good running start then. We're still going to go through everything just slowly to make sure that everyone has it. So what Colab is essentially what we use internally to develop TensorFlow and also to do a lot of research at Google, which is our own hosted version of IPython Notebook. So you can use, if you've got your laptops here, you can use it to run along as I do these, or you can just watch it and we'll have some time at the end for you to go through and do it yourself. But you can access this by going to colab.research.google.com. I should mention you're actually very fortunate because this has only been released by Google essentially at the end of last year, beginning of this year. And it's a really, really excellent tool having this hosted. To start off with, you can sign in using, you should be able to sign in using your personal accounts and you'll be able to connect to a backend. But for some of the later assignments where you're going to need more computing resources, you'll be explicitly whitelisted to give in more resources so that you can actually train some of these more sophisticated models we're going to be looking at. So you can be hosted with Python 2 or Python 3. I would recommend generally using Python 2 because even with TensorFlow this is still better supported, but you have the opportunity for both. And this is the kind of thing you're going to be presented with when you log in. So we've got this signal here that says that you're correctly connected to the back end, which is going to happen automatically for you. But if it is disconnected for any reason, you can just re-click on this item. It'll reallocate you a server on Google Cloud, and it'll reconnect you to your TensorFlow backend. I'll probably skip through this a little faster since most people are familiar with IPython Notebook, but to give you a general idea, everything here is either a code cell or a text cell. For the code cells, you can run anything that's Python. You can run a few extra functions that we'll see. And you can also run direct shell commands, which is going to allow you to install other libraries on the computer if you actually need to do that. So in order to run a cell, your options are Shift-Enter or Control-Enter, or using this play button on the side. And then the output from the cell, okay, so you can see here that I'm actually not connected to the runtime in this Colab notebook. So I can just click on Connect. And now I have my backend. This should be able to run. And very obviously we get 10. Text cells also work very similarly to an IPython notebook. These are very, very useful. I would get in the habit of using these to comment as you're going along. This is also helpful if you're working with other people. I mentioned that one of the things that makes this particularly good, and the reason it's used at Google over IPython notebook, is that you can collaboratively work on this. This is where the name Colab comes from. So if this link was shared with somebody else, then we can both work on the notebook at the same time. Leaving some text cells around is going to make your life a little bit easier. And you can also put in LaTeX, which is again more important when we're starting to be implementing formulas in TensorFlow. Again, pretty basic, but if a cell is running long, you can cancel it halfway. You can also restart the runtime. So sometimes, since TensorFlow is running at a lower level than Python, it can hang in a way that you won't be able to stop it through this. If that happens, go to runtime and restart the runtime. And that will give you everything from scratch. You lose all the saved state because that actually resets the Python runtime. You also have access to system commands, which you won't need to use too much, but in case you want to import other libraries, other Python libraries which aren't built in by default, this is going to be important, and we'll show you how to use that in a second. Yeah?
What are the differences between this and DataLab?
That's a great question. So DataLab is a version of hosted IPython Notebook on Google Cloud, and Colab, which is also very similar to what Colab is here in the public-facing version. The best answer to this is that Colab was our internal version and Dataflow was made by Cloud specifically to be externalized. And so they are very similar, but the feature set is not exactly overlapping. I haven't used DataLab as much, so I'm actually not familiar, but I believe the collaborative nature is not there, but I may be incorrect on that. The other thing you have, which again you have in IPython Notebook, is that you have the ability to use HTML, which we will also be using to help understand what's going on in some of our Python graphs. Or you can put things like this. You may or may not get bonus points in assignments if you put little scrolling text. It depends who's marking it. I will give you more points. I'm not actually marking any later assignments though, so take that with a grain of salt. But obviously you can also do this programmatically, which is going to be very helpful when you're writing a TensorFlow model, because visualization for all machine learning models is always the key to understanding what is going on and debugging what's going wrong. And then you all have these nice things like tab complete. And you can have interactive outputs. It's not clear to me how this is meant to be interactive, but there are also interactive outputs that you can use as well. All this is to say you don't need to use any of this functionality necessarily for the assignments, but a lot of it will make your life a little bit easier and a little bit more fun. You can also, this is also integrated with Google Drive, so it's a good place to save many copies, save frequently, and you will minimize some of the risks there. Okay, so here is the interesting thing where it comes to shell commands. So as you saw before, exclamation points allow you to run shell commands on the machine that this is running on. So if, for example, you want to upgrade TensorFlow to the nightly build, which is something you might be interested in doing, you of course first connect to the runtime. And you'll see that this will go through and actually install the newer version of TensorFlow for you. On this point, most of the assignments will be, they've been made assuming that you are using the current version of TensorFlow that is running on these machines. However, if you want to use some of the newer features of TensorFlow, which can be very helpful, one which you might want to look into is called TensorFlow Eager Mode, and it can make debugging a lot easier for complex models. You would need to run the nightly build, and so you would have to run this kind of thing. And in similar ways, these two introductory collabs are linked directly off the landing page, so you can go back to these. They're very easy to access, and it just shows you how you can install these different libraries. If you have favorite Python libraries you want to use, the standard binary only comes effectively with TensorFlow installed, so if you want any other libraries, you will need to install them. Okay, any questions on Colab so far before we have a look at some of the formulas Matteo brought up earlier in the talk? Yeah?
Do we need to upgrade TensorFlow every time we restart?
Yes, so if you want to be using the nightly version, you would have to run that every time you restart your runtime. Any other questions? Yes?
Oh, is there environment management?
Oh, like virtual env?
Yeah.
No, but effectively you will get, since you get a new runtime, a fresh one every time you open a new collab, you could simulate this by essentially having different documents for different things. So it's probably possible, but I haven't tried it. I don't know anyone who has. Any other questions?
I'm probably getting quite thinking, but is there a decent command that would help you see all the globals, like what the global variables are that you've done? Because sometimes the problem is that when you've gone through this thing multiple times, because there's so much global state, unless you have everything in functions, which the idea is that you don't really do that, you can play yourself in knots sometimes.
Yeah, so this is a really good point. If people are not very familiar with IPython Notebook, one of the things that can make debugging harder and bugs that come up quite often is that you set a variable in a previous cell, you maybe delete that, you forget about it, but it's still globally set in the Python runtime, and you have these very odd issues to debug. There is where is it? Okay, so in Colab, the closest thing that can help in this is you have a history and an executed code history so that you can see what has been run in order from the cells. And so it's one thing that you can do to flick back and see if there's anything that stands out. Aside from that, it is a problem, and just generally good code health. And if something goes wrong, resetting, as I showed before, if you reset the runtime, that obviously clears the Python global state. So if you have any odd transient errors, that can help clean that up. Any other questions? Nope. Okay. Oh, one other thing that you might also find helpful is if you have a cell, you'll sometimes run into an issue, especially in the later assignments, where you have a lot of somewhat dense code and the collab's going to go quite large. Colab gives you, nope, maybe it doesn't in this. Okay, I take that back. Not all of the internal, not all of the internal features are external yet, but hopefully that will be soon. Okay, so this is code that you might find useful while you're developing, which is going to allow us to visualize the graph in a nice explorer and making something. So we'll have a look at a very simple TensorFlow graph in code and then actually see it rendered. Okay, so this is a very, very simple TensorFlow graph. Don't forget to connect to your runtime. Okay, so that's executed correctly. And now you can see here we have 2 multiplication operations and 4 constants. So it's obvious to everyone why there is 2 multiplication operations there and 4 constants. Does anyone want to suggest a reason why that might be? Yo.
I don't know the answer, but it's not legible from the back.
It's not legible from the back? Thank you very much. That is still very useful to know. Let me see if I can zoom in for you. Is that a little bit more legible? There we are. So this shows everything that's been written into the Python graph so far. The reason that happened is because I ran the cell once without showTFGraph there, and then I ran the same cell again after I'd written showTFGraph. So the first time it creates 2 constants and a multiplication operation, and then the second time I ran that, it creates another 2 constants and another multiplication operation. And what we've now got in the graph, X refers to the second one that was created, and we've now orphaned part of our TensorFlow graph. We have something in the TensorFlow graph, but we have no Python variable that refers to that multiplication node anymore. So if this happens, it's not actually a big deal because that node will just sit there and won't get executed if we don't have a Python reference to it. But that's the reason that there's 2. And you'll see throughout here, there's a tf.reset default graph. So if you don't explicitly tell TensorFlow what graph to put things into, it has a default graph that it'll put it into by default. If we run reset default graph and then run this again, there should only be 1 multiplication and 2 constants, which is what we see there. So we'll go down and see. This tends to only be useful, it's a kind of last resort debugging mechanism, to be honest, because you'll see that as we start to get more complicated functions, the graph becomes very complicated very quickly. The most useful advice I can give you to successfully completing the assignments that you'll be given is that it's much better to not make mistakes in the first place. And so if you have a chance to pair code, work with a friend and try and make sure that everything is right all the way along, you'll be much better off than trying to debug at the end because it is notoriously hard. Okay, so this is just what we were looking through in the slides in the first half with Matteo. And this is generating some random data that is linear with some noise added. And then these structures that we saw before. So here we've got 2 placeholders where we're going to be putting in the X's and the Y's that we're going to be training on. And so we have a pretty simple graph here. We have X's and Y's because that's all we've constructed so far. However, now we're going to create a linear model. Actually, I'm sorry, I realize that text is actually quite small. Can people see the text up the back? Not really. Let me... I don't know that I can actually help you out here. You can do the... yeah, that's... Is that any better? I think it's just going to be hard to read this much code from far away, so you'll just have to trust me that I'm telling you the right thing. I'm not going to lie to you. Oh, dear. Okay, I deliberately left this in to show you how difficult it can be to debug TensorFlow code. And so I'm going to follow my own advice, and I'm just going to restart the runtime and go from the beginning, because I'm fairly sure that should have worked. If not, and there you go. Reset default runtime. Okay, so this is what the graph looks like for closed form linear regression. So you can see now that there's quite a lot of fundamental operations that go into even something here which is relatively simple. And you can see that the variables in the graph, the W and the B, here are highlighted in blue. And these larger boxes that you can see here actually are groups, and if you double click on them, you can go and see the operations that are within that entity within the TensorFlow graph. And then you can see, as Matteo claimed, if you run this, you do get the closed form linear regression solution to that particular set of data. So we're getting to the end now. I'll skip the rest of the lecture code is in here, and this all runs straight up. I'm going to share this Colab after the lecture in the Moodle. But for the moment, is there any questions before we finish up? Yeah.
So you have this really nice interactive graph. Do you have anything like that instead of matplotlib as well?
Do we have anything like that instead of matplotlib? No. I really wish we did, but we don't.
You can use TensorFlow to visualize the variables, like instead to plot the values of the scale. That might
Could you say that again?
You can use TensorFlow to plot the values of scalars throughout. That might be a good thing.
Yes. So for TensorFlow variables, TensorBoard has some visualization capabilities, although it's not clear to me whether you will be using TensorBoard in these exercises. I'm not sure at the moment. Yes.
But this short TF graph looks awfully like TensorBoard visualization.
It is. This is used within TensorBoard.
Okay. So can you then also visualize like training pointers, like losses? So it basically has the same functionality as TensorBoard.
This is a particular widget that there's an internal version which does this properly. This is a kind of like external hack that you're essentially pulling from a TensorBoard instance just to get a nice graph down. It would be in theory possible to get the other stuff too, but I won't be able to supply you with that code.
You mentioned this runs in the cloud. Can we run it offline, like if we're trying to work somewhere without internet?
I don't believe so. Not for the external version. You will have to have an internet connection.
Can we download the notebook from it in Jupyter and then reload it in code?
Yes. You'd be responsible for making sure that your component, like your runtime, your Python runtime, has the same version components. So just be careful of that drift, but otherwise you should be able to run them in a normal IPython notebook. Yep, same one. Any other questions? Yeah.
What's the playground? The file opening playground?
If you open in Playground here, that allows you to open a IPython notebook and be able to play around with it, but it doesn't save a copy in Google Drive. So normally when you start a new one, it'll save a copy in Google Drive, but if you just want to play around with one that you've been sent, you can open it in Playground to actually execute it without saving it.
What's the best way to group your graph variables? Is it with name scope or variable scope?
The best way is generally with a named scope. As much as you can do that, it also does help debugging a lot. It's a very good practice to use. So yeah, I put named scopes on everything, and just while we're on the subject of good things to do, often commenting tensors with their expected shape in the Python code can be very helpful to make sure that you are calculating the quantities that you think you're calculating. Any final questions?
Do the runtime sessions run out after a while, or do they kind of sit there indefinitely with that?
As long as you have your Colab open, it should just sit there indefinitely in the back and time out. If you have we'll see as the course progresses, if you have very long-running jobs, we'll need to make sure that nothing fails, but also once you've been whitelisted, you'll actually have specific machines which are for you guys that shouldn't go down.
When you say as long as your Colab is open, what if your internet connection dies?
If your internet connection dies and you lose connection with the backend, my guess is that you would be able to reconnect to a fresh kernel, which means you'll lose any state that's going on. So yeah, don't do this anywhere you have a really sketchy internet connection. But I was going to say, I hope UCL has a pretty good one. Last one, yeah. What, sorry? What free resources do you have access to on here? I think it's probably not the smallest instance on Google Cloud, but maybe the second smallest instance, which gets spun up in this free version. When we get you your whitelisted access, I think it's either going to be a GPU instance or an 8 CPU instance. All right, thanks very much for your attention this morning, and good luck with the rest of the course.